Hello, today we're looking at lecture number 10, which is going to deal with the deflection of beams. And the deflection of beams is essentially about the sagging of beams. And if you can see this ruler, when you put a load on a beam, and I've spoken to you about this before, a beam deflects. Everything deflects. Everything moves. Even though it doesn't appear to, it does move fractionally or a lot. So deflection of beams, these are the symbols that we use in doing the calculations we're going to do today. And there is a mathematical relationship between slope and deflection of beams. So if I drew a beam, a simply supported beam, like this, with just say a central point load, it would deflect like that. And there is a mathematical relationship which you can solve using integral and differential calculus for working out what that deflection is. This is the deflection there, of course, and what the slope of the member is. The slope at the support where the slope is the maximum. The slope at the point of maximum bending moment is 0, of course, because that's at the point of curvature. So the following mathematical relationship occurs between load, shear force, bending moment, slope and deflection. And starting with deflection down there, if you differentiate it once, if you differentiate the deflection, you will get the slope. And differentiating it again, you'll get the bending moment. Again, you will find the shear force on the beam, and again, d4 dy dx4 will give you the actual load, W. So that's an important mathematical relationship in doing deflections. Purely mathematical relationship. Now, Moore's moment area method is spelt out here, giving you the deflection and the slope. You can go through that yourselves for those who are interested. But we can summarize it by saying that the above can be summarized as follows. The slope is the change in slope between any 2 points on the loaded beam is equal to the moment, the bending moment, divided by the elastic modulus and the moment of inertia diagram between those points. That will become clearer as we go through this lecture this afternoon. The deflection, the vertical displacement of a point on a beam relative to the tangent at a second point is equal to the first moment of the bending moment divided by the EI diagram between those points, taken at the first point, the point at which the displacement or deflection is measured. And I'm going to go through these standard cases. I've got 5 standard cases here, and by the time I've been through it and you've done a few examples, I'm sure that you'll become quite polished at doing these problems. So we've got standard cases. I'm going to do 2 cantilevers. The first one with the point load, the second one with the uniformly distributed load, and then 2 simply supported beams, one with the central point load and one with the uniformly distributed load. And last of all, I'm going to do what's called a propped cantilever, which will become evident to you as I go through the problem what a propped cantilever is. So the standard cases, we've got first of all, we're starting off with a cantilever with a point load. Essentially a beam fixed at one end, fixed so that it can't rotate there, and I'm hoping that you can see this on the film, on the movie. So working out you'll all know how to work out the bending moment, yeah, because the bending moment at A is purely the force times the distance, W times L, and there it is. That's the bending moment. So if you drew the bending moment diagram, it has a linear relationship, being a point load at the end. Halfway along it would be WL over 2, because it would be half of L, so it would be half WL over 2. So it's just a plain triangle. That's the area of the bending moment diagram. And the distance from the free end to the centroid of that triangle is 2/3 of L. That's a position, or 1/3 up from the base, but we're working from this end, 2/3 from the free end. Now the slope at B, which is going to be a maximum, so in other words, looking at this, when this beam deflects, because it's fixed on the left-hand side, there is the slope. That's the exaggerated shape of the beam. We want to calculate the slope, which you work out in, the answer is in radians, of course, and the slope is that slope there, whatever that angle is. So the slope at B is the area of the bending moment diagram divided by the elastic modulus multiplied by the moment of inertia of the section. So what do we have? Pretty straightforward. WL times L times a half. That's the area of that bending moment diagram. WL times L times a half is the area of the bending moment diagram divided by EI, which gives you the slope. Pretty straightforward. WL squared over 2EI. That is the slope in radians of the beam at the free end. Now, the deflection at B, and this is the deflection, of course, delta, that's the deflection there, is the first moment of area of the bending moment diagram divided by EI. The first moment of the area of the bending moment diagram starting from the free end. So we have WL times L times a half, or L over 2, or times a half, sorry, times a half gives you the area of the moment diagram, times the lever arm to the centroid of that moment diagram, which is 2/3 of L, 2/3 of L divided by EI. So the formula then for the deflection over there is the sum of this, WL cubed over 3EI. And if you had a real case that you wanted to solve, and you substituted a W and a L in there, you could actually work out what the deflection is. And you'll be doing that in the tutorials with me. So moving on to the next page. Secondly, we're going to do a cantilever with a uniformly distributed load. Now the difference between a uniformly distributed load and a cantilever and a point load at the end is this bending moment diagram, which is partly parabolic. Just for simplicity's sake, if you took this enclosing rectangle, this area is 1/3 of that area, and this is 2/3 of the area, making an area. So that's an easy thing to remember, but you can check this through with your notes. Now, the slope at B, the slope due to the cantilever, as I said in the first problem, bending down like that, the slope there is the area of the bending moment diagram divided by EI. What is the area? WL squared over 2 times L times 1/3 of this enclosing area. And that's the third there, times the 1/3 over EI, which gives you a slope of WL cubed over 6EI radians. Now, the deflection at this point, the deflection at B, at the end of the cantilever, is the first moment of area of the bending moment diagram divided by EI. When I talk about deflection, of course, again, that's the deflection. It's the amount that the cantilever is sagged. So, first moment of area of the bending moment diagram, the area is WL squared over 2 times L times 1/3, times the distance from there to the centroid of that part parabola. And you'd find that in tables, but the actual fact is that it is 3/4 of L. And that's why we have WL squared over 2, this arithmetic there, which gives us the deflection. And when you sum all that up, you end up with a deflection of WL to the 4th over 8 EI. Right, third case now is a simply supported beam with a central point load. I'm sure you'll all remember that the bending moment, maximum bending moment for that setup is WL over 4. There it is. And that's the moment diagram. You're all familiar with that because we've been over that many times. The distance to the centroid from the support is 2/3 of L over 2, because this dimension from A to C is L over 2, so it's 2/3. That's the centroid of that triangle, that bending moment triangle. So the slope at A, at the support, the left-hand support, is the area of the bending moment diagram between A and C. Between A and C, this area there, which is pretty straightforward. WL over 4 times L over 2 times a half. That's the area of the triangle divided by EI. Do your arithmetic and you get a slope of WL squared over 16 EI at support A. That's the slope at that point. Now, moving on to deflection at C, that's at the center of the beam. That's where your maximum deflection will be. First moment of area of the bending moment diagram between A and C about A. So we've got the area of the bending moment diagram, which is WL over 4 times half the span times a half. That there is the area of the moment triangle, times the lever arm, which is the 2/3 times L over 2. So that is the 2/3 times L over 2, all divided by EI. Deflection for a simply supported beam with the central point load being WL cubed over 48 EI. And you can find that in any sets of tables on engineering deflections and formulae, etc., slopes. You can confirm those. But you can now work them out yourself. We get on to case number 4, which is a simply supported beam with a uniformly distributed load. Now, here we have a plane parabola, as you are well aware, because our maximum bending moment is WL squared over 8. For a simply supported beam with a load of W per unit length, our maximum moment is WL squared over 8. We have a parabolic bending moment diagram. And the area of this moment diagram, just going back to the cantilever with the uniformly distributed load, that just is a matter of interest, just to get you interested in the geometry of the whole thing. This was a third. If you had a parabola like that, that's what your moment diagram looked like for your cantilever with a uniformly distributed load. The other 2/3 are there, actually, as I showed you earlier. So we're dealing with the 2/3 in this particular case. That's why we have WL squared over 8 times L over 2 times 2/3 of that rectangle, because that's that moment diagram there, all divided by EI. The slope then at A is little w L cubed over 24 EI. So if you wanted to work out how much your beam was sloping, you could plug your known data into there and do the computation. Now, the deflection at C, which is at the center, is again, repeating myself, the first moment of area of the bending moment diagram between A and C about A. So that is what we have to do. The first moment of area of this bending moment diagram between A and C about A. So we take moments from there to there. The dimension from there to the centroid of this moment area there is 5/8 times half the span. That's the dimension to the centroid of that area. All divided by EI. So we have WL squared over 8, WL squared over 8, times L over 2, times 2/3 is the area, times 5/8 times half the span, times L over 2. Consolidate all that and you come up with that standard formula that most structural engineers would be able to tell you if you woke them up at 1:30 in the morning. They'd actually just repeat it quite easily because it's ingrained in their minds. Deflection for a simply supported beam with a uniformly distributed load is 5 WL to the 4th over 384 EI. Okay? So that's a standard deflection. Those are the 4 standard cases I'm going to cover today. There are, of course, methods using Moore's theorems of working out deflections in greater detail at any point along a beam, which are pretty useful, but largely supplanted by the use of space gas or other software these days. But it's good to have a rudimentary knowledge of deflections and slopes. I'm now going to do a problem that often comes up on construction sites, funnily enough, where you have to prop a beam, and of course it'll come up in consulting engineers' offices as well. But the example says, using Moore's theorem, calculate the force P in a propped cantilever carrying a uniformly distributed load of W per unit length. So we've got a cantilever there. It has a uniformly distributed load on it, and it's got a prop propping up the end so that this cannot deflect. There can be no slope, no deflection at point B. What we have to do is find out how much of that load on the cantilever actually ends up going down into the prop P. So, solution: to find the force P, it must be assumed that the deflection at B equals 0, and that's what I've just been going on about. We assume that that doesn't move down at all. Therefore, the deflection at B due to the UDL and P must both equal 0. So there's no deflection at that point. Okay, essentially what we're going to do is we're going to work out draw up the deflection for a simply supported beam with a prop on one end, and I'll go over that, with the UDL on it. Equate those two because there's no change in height there, and we will then be able to solve for the force in P. So our first bending moment diagram then is the one we've just been doing earlier on, case number 2. There our parabolic bending moment diagram is looking only at this condition. And we have a UDL on there. We've removed the prop. That's what we've got. We've got W per unit length. W per unit length. Okay? And we end up with a bending moment diagram that looks like that, which we did earlier in case 2. We then, so the deflection due to the UDL, which we worked out earlier, WL squared over 2 times L times 1/3 of that enclosing rectangle gives us this area, times the distance from the free end to the centroid of that area, 3/4 of L. And we get WL over 4, WL to the 4th, divided by 8 EI. Now we look at the deflection for the point load, and this is what our moment diagram looks like, because what we're looking at now, I'll draw it the way we actually think about it. There the cantilever is. We've taken the uniformly distributed load off it. We've put a force P onto the span L there, and we end up with this moment diagram. Notice it's drawn on the tension side because that prop's tending to bend it that way. So there's our moment diagram for a cantilever with just a prop on one end, but we're propping it from the bottom going up rather than putting a load on from the top. So the deflection due to P then is PL, force that could have been W, but it would confuse the issue, so we're calling that P for the force in the prop, times L, times a half, because we want the area of that moment diagram, times 2/3 of L, which is the distance to the centroid of that triangle, all divided by EI. So the force, the deflection due to the P, if we allowed it to deflect, would be PL cubed over 3EI. Now, for no movement to take place at this point here, we can equate the deflection due to the uniformly distributed load with the deflection due to the force in the prop. And that's what we do down here. Therefore, WL to the 4th over 8 EI, which is the deflection due to the UDL, must equal the deflection due to the prop, that PL cubed over 3 EI, because there is no deflection, so they equal each other. So the force in the prop, then, you solve this, transpose this equation, and you'll find that the force in the prop is 3/8 of WL. In other words, the force in the prop is 3/8 of this total load. And there you have it. Thank you.